assuming. Right. All right, so let's quickly recap of what we talked about in terms of the phase diagrams. Remember, phase diagram by definition was graphical representations of the constituents of the soil, right? And then the way that we essentially characterized it was through the layering of the constituents. Remember, we talked about we have the view through the system of melting, merging, and extraction. If you melt all the solid grades into one layer and extract the air and place it into a different layer, and also extract the moisture and place it into another layer, you have different constituents of the material there, right? And on one side, you're looking at information about the volume. The other side, you're looking at the information about the weight of the material. And ultimately, what you end up with is your phase diagram engine. And then we talked about the four components that we have in terms of the phase diagram, in terms of the phase relationships, in fact. Remember, three of them were volumetric relationships, and one of them was weight relationship, right? So the volumetric relationships were void ratio,
degree of saturation, and porosity.
Degree of saturation and the porosity of the material. Remember, the degree of saturation essentially separates the soil mechanics into saturated soil mechanics and unsaturated soil mechanics, right? So that also influences the stiffness properties of the medium that you have. And then you have the void ratio. What was a good example of the void ratio, or where we use the void ratio? For the settlement analysis, right? We talked about the settlement analysis, and essentially what you have to do is you have to plot the information relevant to the stiffness properties, or the stresses, in fact, as a function of changes in the void ratio. So you have void ratio on the y-axis, and you have the log of sigma prime, which is the log of the stresses, and that shows you the differences or changes in the stiffness properties associated with the changes in the void ratio, and how you can correlate that to the settlement analysis. That would be your chapter 9. All right, what else we had? We had the water content, right? What was the water content? How do you calculate the water content?
Weight of water divided by weight of solid.
Weight of water over weight of solids, right? So you have that in terms of the equations, and remember, water content, degree of saturation, porosity, they will be reported as percentages. And then you have the decimal for the void ratio. All right, so those are the main parameters and characteristics that we talked about in our previous lecture. But today we are going to talk about a different topic, and that is the soil texture. All right, so let's assume that I grab a fistful of soil in my hand. What are the parameters that comes to mind when you're looking at the soil in your hand?
Forecast.
All right, so one step back. What is soil?
An aggregate.
This is one of those intuitive things that you know that you think you know it, but you want an engineering definition for that. What's a soil?
Aggregates that are held together.
It's a mixture of aggregates.
We're only talking about soil, so we're not talking about the multi-phase systems. This is coming from your geology. By definition, soils are agglomerates of materials, in parentheses, minerals and organic matter, that is found close to the Earth's crust. I'm assuming that all of you passed your geology course and your All right, so agglomerate of materials, which is basically sediments and organic matter that is found close to the Earth's crust. So what does that mean? It means that we are not interested in the material that are 2 miles down in the soil. We are looking at what is happening close to the surface. Right. What else? So that was the definition of the soil that you're familiar with. Now let's go back and talk about the soil texture. We're talking about the soil texture. Grab a fistful of soil in your hand. You look at it. What are the things that comes to mind?
The size of the particles?
Excellent. Particle size. What else?
Moisture content?
The
We're
field
talking about the soils. So we're looking at the soil texture. The parameters that comes to mind are particle sizes, If it's large, if it is small, if it's
Hardness?
intermediate, something in between, clarity. Shape of the grains, let's call them the geometry of the particles. Yes.
Hardness?
Hardness, by looking at it, you probably can't tell, but
Plasticity?
that's an information that you can get from testing that. Plasticity is also has to do with the surface activity, that's another thing.
The feel to it.
The feel to it, all right. So the feel to it, part of it would be the particle size, the other one would be the geometry, if it is sharp-edged or if it is rounded. That's the feel of it, and that's the geometry. What else? Grading, or particle size distribution, right? So these are the parameters that comes to mind when you're looking at soil texture. So, in very simple terms and in very crude terms, soil texture is the way that soil feels in your hand. Right? But that's a very crude way to do it. Now let's talk about it in terms of the engineering properties. All right. So, we're talking about the particle sizes. You can essentially separate the soils into fine-grained soils and coarse-grained soils. Right? What's the sieve number that corresponds to fine and coarse-grained material from your materials class? So you have sieve number 200, which essentially separates the material that are smaller than 75 microns or larger than 75 microns, as you're familiar with. Right? So in terms of the sizes, let me go one step back. If you're looking at the particle sizes, in terms of the definitions, we have fines and we have coarse-grained material. On the fine side, we have clay material and silty material. Right? So silt and clay falls under the fine-grained soils. For the coarse-grained soils, what do we have?
Sand.
You have sand, you have gravel, boulders, and pebbles. Right. So those are essentially the different definitions that we have with respect to the particle sizes. All right. So just to simply go back and revisit what we talked about, we are looking at particle sizes. Essentially, we are looking at sieve number 200 or materials that are either smaller or larger than 75 microns. Right. 0.075 millimeters. So that's basically in terms of the particle sizes. So let me just plot that down for you to see what are the received numbers and what are the particle sizes. So essentially you have fine-grained soils, and you have coarse-grained soils. Under the fine-grained soils, you have silt and clay. Here we're looking at the USCS definition, Unified Soil Classification System. Later on when we talk about the AASHTO classification, the definitions are going to be somewhat different. All right, so you correctly pointed out that we have sand, Alright, so we have sieve number 200, and the value that corresponds to that was 75 microns, or 0.075 millimeters that we talked about. So sand, gravel, cobbles, and boulders there. We have sieve number 4 here, which essentially separates sand and gravelly material. The particle size that corresponds to that is 4.75 millimeters. And then you have number 3, sieve number 3, or number 3-inch sieve, not sieve number 3 rather. And the value for that would be 75 millimeters. We really don't have much information above the gravel size for the geotech applications. All right, so this is with respect to the particle sizes. Now let's think about the mixture. Remember, we are looking at coarse-grained soils and fine-grained soils. All right, what's the definition of fine-grained soils again from your materials class? You know that these are going to be material that are smaller than 75 microns. But typically, we are looking at it as percentages. So if you have a soil mix that more than 50% of it is smaller than 75 micron, we call that fine-grained soils. If you have a mixture that has less than 50% passing sieve 200 material, that is called coarse-grained material. The engineering behavior of coarse-grained material and fine-grained material are essentially very different from one another. And we're going to separate them and we're going to talk about them individually. But for that, we need to figure out what are the exact definitions of each of these individual components here. All right, so let me just quickly write that down, what we talked about in terms of the definitions before we move forward with characterization of the coarse-grained material. So, coarse-grained material it's more than 50% retained on sieve number 200. How about the fine-grained soils?
Less than
Notice that I cautiously use the words retain and past. You have to be very careful with this kind of definitions because your gradation charts are going to be flipped over when you're looking at the percent retained or percent passing. We're talking about the sieve and sieve analysis. I'm sure that you're familiar with that from your other courses, but let's quickly recap of what we mean in terms of the dry mechanical sieve analysis. What does that entail? So essentially for the sieve analysis, you know that you have dry material. First of all, you have to have dry material. And you have assorted meshes, right? So you have meshes with larger eyes or wider openings placed at the top, and then progressively becomes smaller and smaller as you move down the stack, right? And then at the very bottom of it, you have the pan. You have sieve number 200, and then you have the pan in there to collect all the material that are passing the sieve number 200, right? Make sense? So you're familiar with that process there. So through the process of shaking of these sieves together, what happens? Portions that are larger stays at the top, and the ones that are smaller pass through these sieves. And ultimately what you have to do is separate each sieve, weight the material, and figure out what would be the percent retained, and then find the percent passing, right? And for your gradation curves, what do we typically plot in our gradation curves? Remember, you typically plot your percent passing versus the log of diameter, right? So those are what is coming from your other classes. We are going to go through that again quickly later on. All right, so this is our definitions that we have in terms of what the fine-grained materials are, what the coarse-grained material are. And then later on we are going to see the physical properties of the coarse-grained soils and the fine-grained soils. And after chapter 4, we'll talk about the mechanical properties of that. So, and that would be the case that you'll see the application of the solid mechanics or your mechanics of materials and the structural analysis that you see in particulate soils or particulate media. They're entirely different. So let's quickly go back and talk about the mechanical properties that you can expect from coarse-grained soils. Let's start with parameters that influence. parameters that influence the mechanical behavior of coarse grain soils. All right, Robert, you told me one of those. What was the first one that you said?
The feel to it?
The feel to it. Let's talk about maximum aggregate size present in the mix. In the industry, this is also called the particle top size. So if they tell you that what is the particle top size in that specific mix, you have to go and look at your gradation curve and see what was the maximum aggregate size in your mixture. Right? Make sense? What can you tell me in terms of the mechanical properties of particle sizes? Think about it intuitively. You have very fine soils and you have big chunks of aggregates, right? If I have fine grain soils, and I go there and stick my foot there, I can see my footprint right underneath it, right? So the deformation characteristics are not going to be as desirable as coarse grain, solid soil, right? So the larger would be the particle size, the higher would be the stiffness properties. This is the way that you can essentially correlate it and understand this. So the first one is very simple and very intuitive. What was the second one that you mentioned, Robert, in addition to that field that you said? That actually came from Jacob on the other side. That was the particle size distribution, right? Alright, so what is the particle size distribution? You're essentially looking at the assortment of the sizes. You have larger particle size, you have intermediate particle size, you have a smaller particle size. So when you hold the soil in your hand, you can essentially see that. And that would be, again, a crude way to address that. Since we're dealing with the engineering side of it, we have to look into characterization of that. We do it based on the sieve analysis, and we look at it based on the gradation curves. Now, we have different types of gradation curves, as you may be familiar with. We have well-graded soils, and we have poorly graded soils. So let's define those and see what these mean, and see what are their contributions to the stiffness properties in general, or the mechanical properties in general. So let's have the first definition, and that would be the well-graded gradations. So well-graded gradations consisted of well-graded gradation consisted of small particles, intermediate particles, and large particles. The way that you have to correlate this is with what we talked about previously. Remember, for the coarse grain material and fine grain material, we had silt and clay, we had gravel and sand, right? So you want to have pretty much all of these within the mix so you can essentially maximize the density or maximize the packing. Let's go 2 steps back. Remember in our first lecture, we talked about the load transfer mechanism in particulate soils. What was the load transfer mechanism? How does the load transfers within the medium in the soil? Remember soils, you don't have any glue in between, right? You have solid grains. For instance, for concrete, what do you have in concrete? You have mortar, you have aggregate there, right? So in that case, you do have a glue. You have something that provides adhesive bonding between the aggregates. Agreed? Similar to asphalt. What do we have in the asphalt mixture? You have aggregates and you have binder, right? Or bitumen, or tar, or whatever you call it, right? So you have essentially a glue in between to hold those particles together. How about for an unbound soil? Do we have any glue in between? We don't. So we have to bank on another mechanism. I don't have adhesive bonding between the binder and aggregates. I don't have adhesive bonding between the mortar and aggregate. I don't have adhesive bonding between the lime, fly ash, emulsions, foamed asphalt, or any other medium that you have in there. It's just the soil and the water, right? So the load transfer mechanism is through frictional properties and the interlocking effect. So that's something that essentially has to come to your mind when you're looking at the specific transference of the loads within the medium. So anything that contributes to friction is going to be a player here. So we are looking at particle top size. We're looking at the gradations. For the gradations, I'm looking at the well-graded material. Consider the small, intermediate, and large particles. In this specific gradation, the small particles fit in between the intermediate particles fit in between the large particles, and ultimately you minimize the void spaces and fill the void spaces with the solid grains. You know that the weight of the solid grains are higher than the weight of the air, right? Therefore, what happens to the mass, total mass, would be maximized, right? So you can essentially pack more solid grains per unit volume. So what happened here? More density, right? Density was mass over the volume. So essentially at uniform or unit volume, I was able to pack more solid grains. Now what happens if I have similar size spherical particles? There's going to be big huge gaps in between, right? If I pack them inside the 6-inch mold or cylinder, right? So what happens to the density there? There's going to be a lot of air void in the structure, and therefore, right, the density is going to be much lower, the packing will be much lower, the stiffness properties will be much lower, the deformation potential is going to be much higher, right? So this is the way that you have to essentially correlate these concepts together. So we have well-graded gradations. So let's take a look at how that would work. So let's plot the histogram of that. What was the histogram from your statistics? Too long ago? So this is essentially the histogram that you have. This is your particle size. Obviously the particle sizes or the bins that we have here represent the smaller particle size. As you move towards the right-hand side, these are larger particle sizes, right? So what do we have here? It basically tells you that you have small particles, you have intermediate particles, and you have larger particles in the mix, right? How does the distribution look like in this case?
Like a bell curve?
Yes, it's called the bell curve, or if you recall, at some point you call that normal distribution as well, right? So that would be your histogram, and that would be the distribution that you have in there. Now what happens if I plot the cumulative distributions? This would be your log diameter, and this would be the percent passing that we have in our gradation curve. If you plot this, you end up with an elongated S-curve. This is log D. D is the diameter of the particles. This is where you get it from your sieve analysis. And percent passing is what we got it from our sieve analysis again, right? So what do I have here? I have an elongated S-curve. Elongated S-curve essentially says that you have small particles, you have intermediate particles, and you have large particles in your mix. And that would be favorable because it will provide more contact points. And once you have more contact points, you have more contact area. Once you have more contact area, what happens to the friction?
Increase.
Think about it in terms of, again, back to statics. How do you calculate friction? Yes, you need to know the normal force, and you need to know the coefficient of friction, right? So if I have larger contact surfaces, therefore I have better frictional properties. Do you agree with that? So what happened here, since I was able to pack more small particles in between the large intermediate particles and more intermediate particles in between the large particles, now I maximize the particle contacts, right? So now that you have the higher particle contact, you have better interlocking effect and you have better frictional forces there. Therefore, your load transfer mechanism is going to be a whole lot better there. All right, so this would be the case for the cumulative distribution that we have here. What's the slope of the cumulative distribution? This is again coming from your statistic. The slope of the cumulative distribution is the frequency. So what this basically means is that you have relatively similar amount of material all along. Remember, we tend to have more, we want to have small, intermediate, and large. There's not much of a change in terms of the slope, as you can see here, the elongated S-curve. The slope of the cumulative distribution curve represents the frequency of the observations. That's coming from your, again, statistics. All right, so that was a well-graded material. Where do you use the well-graded material? Foundations, good example, yes. Where else? In roads, foundation of highway pavements, foundations of airfield runways. In very simple terms, anywhere that you expect load bearing, right? Any instance of when you need to have a robust platform, right? You use a well-graded material. All right. So that was very simple and straightforward. Now let's talk about the poorly graded material and see how we can characterize this one. So in terms of the gradations, now we can subdivide them into uniformly graded soils. This basically tells you that this is a gradation that consists of similar soils particles. All right, tell me how the histogram would look like in this case.
Sharp, concentrated.
Yes, you have the frequency here, you have the particle size here.
This is one big one.
Yes, that's a good way to characterize that. Do I have a bell curve here? Yes. It's going to be a very condensed one, right? Looks more like a wavelet. Do you agree? And Roy, how does the cumulative distribution would look like here?
Oh, like a narrowness.
Yes. Let's call this one condensed S-curve. What can you tell me in terms of the slopes here? Ricardo? Slopes?
They're different for different particles.
Yes, they're very different at the two ends. They're relatively similar at the two ends and very different from the middle that we have, right? And what was the slope? Slope represents the frequency, right? So where is the slope flatter? Where is the slope sharper? It's flatter at the ends, means that There are less material around that particle sizes, and it's much sharper in the middle. And that would be where we have this particle size, right? So contrast that with what we had before. Previously, we had relatively similar slope all along the curve, all along the S-curve that we had. Similar size particles. On the other side, we have uniform gradation consisted of similar size particles, and ultimately in that specific case you have a shortened S-curve, a condensed S-curve, right? What can you tell me in terms of the packing of this gradation? Packing is not so nice, right? What can you tell me in terms of the cavities trapped in between?
Bad.
Omar, what can you tell me in terms of the permeability of that soil?
It's good.
We are looking at uniform gradation here. We don't have small particle sizes and intermediate particle sizes. You just have one particle size in there, for example, ideally. And there are going to be big, huge gaps in between the particles, right? Remind me from your Yen materials class. What are the different types of voids that we have in civil engineering structures or civil engineering materials? You have two types of voids. You have isolated voids and you have interconnected voids, Louisa. There are two types of voids that we have. What is the distinction between them? Which one do we want? Which one do we want to avoid? And what are the applications? Are you familiar with isolated voids?
That's like one random hole, so.
Hopefully not that big, huge
Oh, yeah, no.
gaps, right? What's the purpose of air entrainers that we have in concrete?
Allow for expansion of cold weather.
Yes, and also it basically creates bubbles there, right? It creates bubbles. Those bubbles are small, and they are going to act as quote-unquote aggregates for you. And they're going to reduce the weight of the structure as well, right? So the total weight is going to be lower. You're going to have small voids in there. They're not interconnected. What happens if they're connected to one another? To concrete. It loses its strength, it creates a weak plane. What else? What are one of the most important things that we are concerned in concrete? We are concerned with durability for concrete. So if the moisture gets in there, right, basically creates the bonding between the aggregate and mortar, right? It compromises the strength. So it creates issues with regard to your durability of your concrete. So, going back again, we have two types of air voids in civil engineering structure. Isolated air voids, interconnected air voids. We're talking about the uniformly graded material. You have interconnected voids. What are the interconnected voids resemble? Goes back to hydraulics. Interconnected void in the structure resembles nanotubes or channels of water. That's how it's tied to the permeability. These interconnected voids create channels, small tubes, small nanotubes, if you will. And that allows for the moisture to travel within the soil medium. Now, for this specific case, since we are looking at uniformly graded material, you're looking at big, huge chunks that creates big, huge gaps in between. What can you tell me in terms of the diameter of those tubes? They are much wider, right? So wider tubes, how can you correlate that to the permeability of the soil? Extremely permeable soil, right? What is this gradation good for? Drainage layers, right? This type of gradation is not good for load-bearing capacity. But if you want to design drainable layers, this would be the way to do it, right? instance, is still called poorly graded material. Doesn't mean that it's not a good gradation. It has different applications. We have to figure out what the application for that is. All right. The other gradation that we have here is
Best.
so gap gradation essentially tells you that you have concentration you have concentration of particles in certain size bins and lack thereof in other bins. So let's see how this one would look like. Again, we have frequency here, and we have particle size. Concentration of particles in certain size bins and lack thereof in other bins. So what kind of distribution am I dealing with here? It's a bimodal distribution here. How does the cumulative distribution look like? Two steps. All right. Do it continuously so I can see. That's actually right.
Simple as?
Side pins and
Think about it in terms of the slopes. That would be the best way you can remember this. Is this correct?
Are you missing some?
Yes, it has to be flatter in the middle. Why?
Slope has to be greater because of the frequency.
There's frequency lower.
Exactly. You have to look at the frequencies there, right? So you have to look at the flatter one here and going like that. Do you agree?
yes.
Where's sharper? And this would be flatter. Where do we use gap rated? The field, okay, good.
Field
For the field.
Look at us here.
All right, let me give you an example. Right now, we are doing a project for TxDOT in energy developing areas, the Eagle Ford Shale and the Permian Basin. And these energy developing areas, or energy developing companies, are transferring extremely heavy equipment over the pavements and bridges. What happens if in a far-to-market road with 1 or 2 inches of asphalt and, say for example, 3 or 4 inches of compacted granular layers, one of those heavy equipments with over 200,000 pounds passes over? It will damage the pavement, It will, what happens to the foundation, which is the compacted soil there? Excellent, it would crush the aggregates, right? So what happens when it crushes the aggregates? Yes, what happens to my gradation? My gradation will be messed up, right? The gradation is no longer going to be the same as the way that I designed it. Right? Typically, particle crushing essentially translates into fines generation. There's going to be a lot of powdery material in there. There's going to be a lot of fines in the matrix. So what do you have to do in that case if you want to go and do FDR or full depth reclamation? You have to go in and add particles that has been missing from the mix, right? You have to go back and modify the gradation. You really don't need to add small, intermediate, and fine particles, or small and intermediate and large particles. You just have to go in and compensate the portion that has been compromised, right? And that would be the case that you use the gradation modification, the gap graded, right? So for the gap graded, the application of that would be gradation modification. So let me just quickly recap of what we talked about here, and then we conclude our lecture today. So we are looking at different types of gradation. We are looking at well-graded material, and we are looking at a poorly graded material. One important thing is that when we talk about the poorly graded material, it doesn't mean that we do not use this. We have different applications for that, right? For the well-graded material, those are essentially the elongated S-curve that we have in terms of the gradation distribution, the way that you can identify it based on the slope of the lines. Right? What else is there? You're looking at the load-bearing capacity. Also, the permeability of this layer is going to be low, right? Remember how you characterize the permeability in general. Permeability has to do with the speed of the traveling water molecule within the soil medium. If you elongate the path of the seepage, you essentially see a lot of friction between the water molecule and the soil, and therefore you see more loss. So also your permeability of your soil is going to be a whole lot lower. So well-graded material, great for foundations, they're great to provide a robust platform, they're great for providing a relatively impermeable layer. Now, the second category that we had was poorly graded material. And under the poorly graded material, we subdivided it into two categories. Category one was uniform gradations, and the other one is gap gradation. One thing that you have to be very careful about is when we talk about the uniform gradation, the word uniform has a positive connotation to it, right? When we say uniform, it means, oh, it's good. But uniform, figure out where it is good for. It's good for drainable layers. Drainable layers, drainable systems, sand drains, the drainable layers at the toe of the dam, and all the other applications that we have for the drainage properties. The way that you have to, essentially the way that you can characterize the shape is, or identify the shape is a condensed S-curve as opposed to an elongated S-curve. In simple term, just draw the slopes, and that gives you a good indication of that. And then ultimately we have the gap gradation, which is essentially follows a bimodal distribution here, as you can see. And you'll see a flat line in one side and sharp slopes on the other ends. Right? And the application of this one would be gradation modification. So there's another item left underneath this one, and that would be particle geometry, and that's the topic that we're going to talk about in our next lecture and get into our lecture. Has everyone attended the lab safety workshop? Does anyone have not attended lab safety workshop?